Consider the region bounded by the parametric curve. And here's the parametric curve. Time goes from 0 to 1. It's a loop, goes up and back. There's an arrow to help us understand orientation. And then there's a question. Which of the following integrals will find the volume by use of the shell method when spun around the y-axis? Now notice, you don't have to do any integration on this problem. So when I talk about you won't have to do lots of integration on the exam, this is what I'm talking about. It's about setting things up. Now, just because there's no integration doesn't mean you don't have to think. You probably do have to think. Setting up is oftentimes the most challenging part. And you want to make sure you're following the instructions. We'll be very explicit. We say, look, we want you to use this method. We want you to go around this axis. So make sure you're paying attention. Now, there's 4 options here, A, B, C, and D. Does anybody have an answer for this one?
I'm going to go the other direction and say it's definitely not B, D, or E.
It's not B, D, or E. That's a bold direction to take because it's actually one of those 3.
Okay, go with D then.
Well, someone has put a bid in for D. Anybody else want to put in a bid?
Well, I'm B, C, or E, but too late now.
No, that's all right. Now, the answer is D. And you probably look and say, what? How? Why? So, what are we after? We're after volume, and we're after shell method. So we say, hey, there's a formula for volume and shell method. We say, all right, so what do we need to do? Well, we know where we're spinning around, and we're told shells. So, by knowing where you spin and which method, you know how to slice. You know whether it's horizontal or vertical. And we need to have it be these vertical slices so that when you spin, you're going to form a shell. So we say, okay, we know we're slicing vertically. So we say, okay, well, we need to put our pieces together. And generically we say, what's going on? Well, we have 2 pi. Our radius is how far we are from the axis. And generically we say, well, that's x. The height, well, that's how far up we are. That's y. And the width is our change in x. And for parametric, we say, well, we don't write dx. We say change in x times dt. So x prime of t dt. Now, it feels cheating here when I call the height y. Because you say, well, wait a second. That's all the way down. But you only want a piece of it. And here's where the parametric curves and orientation comes in handy. Because what's going to happen? Well, what's going to happen is when we come in this direction, our x prime is positive, and so we're going to have a net positive for this whole portion. But when we come back in the opposite direction, x prime is negative, so we're going to have a negative for this lower half. And if you add the full strip, subtract out the bottom, that in fact is the piece we're after. But now you just say, okay, so it's x, y, x prime. So you put in your pieces, your x, your y, your x prime. You pull out all your constants. 2 times 3 times 4 times 3 is 72. So 72 pi integral 0 to 1. T minus t to the 4th, t minus t squared, 1 minus 4t cubed. Okay, so a bonus on this one. Ignore none of the above. Because all of these are interesting answers. One of the 4 other answers will give you the exact same value. Which one gives you the exact same value, and why will it be the exact same value? So you have a 1 in 3 chance. And if you don't know which one it is, what would you be looking for? If I said something's giving you the exact same value, you'd think washer method, right? Turns out A has the same value as D. It's the washer method to find the volume. Now you might say, well, what are those other 2 answers? These 2 answers also are the same value, and that's what you would get if you had spun around the x-axis. So even though you see negatives here, you might say, wait, there's negatives, how can I get a positive out? Well, if you look at the sign of 1 minus 2t, it is negative for a good chunk of 0 to 1. It will turn out to be a positive value.
I don't know how good of an idea it is to expose my strategy, but honestly, I just thought shell method has 2 pi's and 3 at the front, so it's going to be some multiple of 3, and so that left you with, and it's in the first quadrant. So
that's a multiple of 3, that's a multiple of 3, that's a multiple of 3, that's a multiple of 3. They're all multiples of 3. But yeah, how should you approach this problem? Theoretically, let's talk theoretically. If you saw something on an exam, don't panic. Take a second and say, look, write down the generic formula and just start filling in the pieces. Well, what does this correspond to? What does this correspond to? What does this correspond to? And then you just put it together. So if you just sort of say, oh, I have to start from the beginning, that can be hard. But you say, no, I have the formula. And just write down your pieces. All right. Any questions? Good. Well, thought for the day. From good old John Ronald Rule. JRR. John Ronald Rule. That's what it stands for. Tolkien. It does not do to leave a live dragon out of your calculations if you live near one. Now, we have an exam next week. That should be in your calculations. It's a bit of a, well, I don't like to use the phrase, it's a bit of a beast, but it's non-trivial. You should make sure you're preparing for it. Don't pretend like it doesn't exist. The exam exists, and it's coming. And so make sure you're ready. Set time aside. This week, this weekend, prepare for it. And so then, come next Wednesday, next Thursday, you won't be stressing out. You'll be relaxed. You'll say, I'm ready. I'm ready for that algebra. Bring it on, Steve. Bring it on. All right. Now, what's our goals for today? Polar coordinates. So we're going to do a quick review from what we did last time. We're going to talk about plotting. Plotting is a lot less sophisticated than you think, because in general, how do we plot? We just pick some points. But we must choose. And we'll choose wisely. Whereas just random points may not give us much insight. Good points will help us figure out what's going on. And then we'll talk about tangent lines in polar coordinates, but then we'll say, it's a lot easier than you think. We just go back and pretend everything's parametric. All right, so quick review from last time's material. This is the same page. When we're talking about polar coordinates, we're not talking about changing the plane. The plane is the plane. We're talking about changing the way we describe location. So Cartesian coordinates, sometimes called rectangular coordinates, because it's really good with rectangles. So Cartesian coordinates has definite advantages in many respects. Great with rectangles, great with lines, beautiful subjects. And it says, if I want to move to a location or describe something, I say, how much do I move in the x direction? Move that far. How much do I move in the y direction? I move that far. And that gets me to where I need to go. Polar says, how is everything related to one central point? So what do? We have a direction and a distance. So the direction is the angle. You start at your center point and you pivot. You pivot to the right direction and then you move forward. Now, some interesting things can happen, but basically you start at the center, and as I said, you pivot to the right direction, and then you move forward. With this in place, you can quickly relate the coordinate systems one to another. You just put them on top of each other, and you say, right triangles, life is good. x squared plus y squared equals r squared, x equals r cosine theta, y equals r sine theta. We mentioned this again, in polar coordinates, you can describe the same point in multiple ways. The radius won't change. The radius is always the radius, well, up to plus or minus. But the angle can change. You can get yourself dizzy, spin around a couple times, and then end up still pointing in the same direction, or you can point in the opposite direction and walk backwards. All right. So that's the coordinate system. Now we will talk about some problems. Sketch the following curves. These are polar coordinates. So we're in the plane. Theta equals pi fourths. Now, we see theta. What don't we see here? R. There's no R. So when you don't see R, what does that tell you about R? It's arbitrary. So when a variable is missing, it's arbitrary. So you say, okay, so if I think of the plane, we're just so used to drawing our axes, so I'll draw the axes here. We say, well, we have an angle. Pi fourths are 45 degrees. And so we have the angle. And then we say, okay, that's the direction of 45 degrees. If we allow r to move forward or backwards, do we include the whole line? Half the line? Just some of the line? The answer is we include everything on that line. So this theta equals pi fourths is the same as y equals x. All right, that wasn't so bad. Okay, r equals 2 cosecant phi. Well, what does that look like? Not so obvious. But let's think about it. What's another way to think about cosecant? 1 over sine. So we could say, all right, well, we can rewrite this equation as r equals 2 over sine theta. One of the things you got to keep in mind is that when we're playing the game of converting, if we're going from polar to Cartesian, we try to think of what things do we like. We like r cosine theta, and we like r sine theta. So if we don't see something in terms of sines and cosines and trig functions, we make it sines and cosines. Okay, now sine theta by itself, not very helpful. We want an r attached to it. How can we get an r attached to that sine theta? Well, we can do a couple things. We can multiply everything by r. I think the easiest thing is to get rid of fractions. Cross multiply. Fractions are dangerous. I try to avoid them. So cross multiplying gives us r sine theta equals 2. And now we're like, r sine theta. We've seen that before. What's another name for r sine theta? Well, because we need to know what it is. Oh, you mean the variable y. A classic mistake. Thank you. Okay, y. Or y equals 2. So when we come to plot it, we say, hey, y equals 2. That sounds like something we can plot. What is it? It's a horizontal line. Y equals 2. Now, one thing you should notice here, y equals 2, very simple description in in Cartesian coordinates, not so simple in these polar coordinates. Different coordinate systems, some curves that are simple become complicated, but also the other direction can happen. Okay, r equals 3 over cosine theta plus 2 sine theta. What happens here? What can we do? Cross multiply, right? The trick's so nice, we'll do it twice. Now, of course, If something works one time, it's a trick. If it works 2 times, it's a technique. So we can think of cross-multiplying. That's a technique, because now we've done it twice. So yeah, let's get rid of our fractions. And the nice thing is when we move it across, these cosines and sines will now get an r attached to them. We like that. So r cosine theta plus 2r sine theta equals 3. Can we change the name of some of these things? The r cosine can be x, and the r sine, what is that? It's going to be y again. Okay, so this becomes x plus 2y equals 3. Well, what is this? It's a line. It'll hit the x-axis at positive 3. It'll hit the y-axis at 3/2, and then you can just connect. All right, last one here. R equals 6 cosine theta plus 8 sine theta. No cross-multiplying involved here. What do we need? Channel your inner pirate.
We need the R.
R. We need an R. Why? Because we can't do much with just cosine. But we can do a lot with r cosine. Same thing with sine. We can't do much with sine. But r sine, we can do it. So how do we get r's? If we want r's there, we put them there. And how do we put them there? Everything gets an r. You get an r. You get an r. Every single term gets an r. Okay, so what do we have? R squared equals 6r cosine theta plus 8r. You don't actually have to make that noise. Sine theta. And all of these are things we like. R squared, what does that become? X squared plus y squared. R cosine theta. Six x. R sine theta. 8y. Okay, x squared plus y squared equals 6x plus 8y. Aha! That's something. Well, There's a lot of squares here. Let's put things together. X squared, we'll move the x across, put a suspicious gap, move the 8y across, put a suspicious gap, equals 0. Now, it gets us a little bit closer, but now you might say, I'm suspicious about these gaps, Steve. Me too. What should we do with these gaps? You can say, well, just write it better. No, there's a reason they're there. What do we want? We want squares. It would be beautiful if these were squares. So we want to complete the square. How do you do that? Well, in other words, this x squared minus 6x, we want to think of this plus something. We want this to be x minus a squared, where a is some appropriate number, or x plus a squared, whatever you want. Now, suppose it were x minus a squared. Well, here, let me put it as plus a, just for generality. So then this would be x squared plus 2ax plus a squared. So that's x plus a squared. So here's how complete the square works. If you have that x squared in front, you say, okay, what's in front of your x term? In our case, what is in front of our x term? -6. That should be 2 times that special number you're looking for, 2 times a. So 2a equals negative 6. So what's a? Negative 3. So you say, okay, square that. Square negative 3? 9. Then this becomes x plus negative 3 squared. So we're going to add 9. That completes the square. But I can't just add a 9 without making sure I do something to keep the 2 sides equal. What do I do with this other gap? What do I need to add? 16. Negative 8 divided by 2 is negative 4. Square that, 16. And then I make sure I do something so I keep the sides the same. And this leads us to x minus 3 squared plus y minus 4 squared equals 25, or 5 squared. What shape have we just found? Circle. Can you tell me anything about this circle? Where's the center? 3, 4. Do, do, do. Do, 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 do. Okay, there's 3, 4. What's the radius? 5. And it turns out it will go through the origin. So there we go. That's the curve. All right. Well, that's going from polar to rectangular. What if we want to do the opposite? All right. We want to convert this into polar coordinates. X minus 3 squared plus y squared equals 9. Now, what are we looking for? Well, as a good rule of thumb, we can do the following. We have x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. If we see x squared plus y squared, that's very convenient for us to replace with r squared. Otherwise, we can just say, if I see x, put r cosine. I see y, put r sine. Now, before we do anything with the first equation, let's just note this is the same thing as x squared minus 6x plus 9 plus y squared equals 9. And we can rewrite that as x squared plus y squared. See how x squared plus y squared, the 9's cancel, equals 6x. X squared plus y squared becomes r squared. X becomes
R sine.
X becomes r cosine. Now, what can you do here?
Can you divide out the r?
Yeah, you can divide out the r. Now, there are some technicalities, but we say don't worry about them. Now, you might say, wait, what are the technicalities? Well, you should worry, what about the r equals 0 case? But we don't worry about that. So we end up with r equals 6 cosine theta. And that's actually a fairly simple expression. So we started with the circle, and we got down to a very nice expression, r equals 6 cosine theta. All right, how about x cubed plus y cubed equals 9xy? Now you might say, aha, what is that? I don't know.
Can you factor out x plus y?
You can factor out x plus y if you remember that it's x plus y times x squared minus xy plus y squared. But if you don't remember that, what can you do?
Oh, divide the...
When in doubt, don't think. Just plug in. What is x? R cosine theta. So r cosine theta cubed. What is y?
R sine theta.
R sine theta cubed equals 9. R cosine theta, r sine theta. Well, if you write this out, that's r cubed cosine cubed plus r cubed sine cubed, 9r squared cosine theta sine theta. You can factor in r cubed out. Now, generally speaking, we like to go and try to write r as a function of theta. That's our basic goal. How can we get down to r as a function of theta here?
Divide the r squared out.
We can cancel off 2 r's and move that across. So cosine cubed plus sine cubed is unfortunately not 1. It's cosine cubed plus sine cubed. So we'll just write it as 9 cosine theta over cosine cubed theta plus sine cubed theta. All right. What does that look like? I don't know. I don't know.
Would we ever need to draw out something like that?
I don't know. Would you need to? No. Would a computer? Maybe. All right, this last one. X squared plus y squared equals x squared plus y squared plus x quantity squared. What can we do? Well, you see x squared plus y squareds. This is making us happy. Because we can replace x squared plus y squareds by r squareds. The x, well, that's okay. We're mostly happy. So we get r squared equals r squared plus r cosine theta, quantity squared. Okay. Now, before we get too nervous, what can we do with both sides? Both sides are being squared, square root. R equals r squared plus r cosine theta. What else can we do? Everything has an r. Divide by r. 1 equals r plus cosine theta. What else can we do? We can move the cosine across. R equals 1 minus cosine theta. Now, this seems a lot more reasonable than that. If you saw x squared plus y squared equals the quantity of x squared plus y squared plus x squared, you'd be like, But if you saw r equals 1 minus cosine theta, you're like, maybe. Maybe. In fact, maybe we could graph that. This seems to like we have a chance to sketch it. But if we're going to sketch it, we should talk about sketching. All right, so how do you sketch? Well, there's the computer approach, which is to connect the dots. Then there's the human approach, which is to connect the dots. You're like, oh, so we're basically computers. No, we're smart computers. See, a computer says, I'll just put 100 dots. And I'm not even going to pay attention to which are the interesting ones. I'll just put down 100 dots and connect them. And if you ever look at quizzes or exams, and you say, how did they make these pictures? That's exactly what the computer did. It just said, I'm putting a lot of dots and I'm just connecting them. But it puts so many dots that you can't tell that it's a lot of individual straight lines. But they really are. They're just 100 small straight lines. It just looks like it's curved. So how do we make our connected dots? Well, instead of many arbitrary points, we pick a few important points. You might say, well, how is a point important? Well, it's important insofar as it says something interesting about the behavior of the curve. And so for us, we're going to worry about basically two things. When are we at the origin? So when does f of theta equal 0? Because that's a very interesting point in polar coordinates. Because everything always comes back to the origin. We're always talking about how we relate to the origin. So if we're ever in a case where f of theta equals 0, that's interesting. And then the other case is, where is f of theta very large or very small. Look for the max or mins. So that's when we're very far from the origin, and that's when we're very, very near the origin. And once we understand those two behaviors, we can get a reasonable sketch of the curve. Okay, so there's a couple of things, notes here. There's some notes here. It's useful to draw arrays where f of theta equals 0. This is similar to asymptotes. We'll get into some examples of what that means. That's most useful when you cross through 0. Pay attention to the sign. So remember, if f of theta is positive, we're moving in the forward direction. And if f of theta is negative, we're moving in the backwards direction. Check for symmetry. Symmetry is a friend, especially as we get into problems involving things like area in our next lecture. So if you see examples where f of theta and f of negative theta are the same, that's an example when you see symmetry across what we call the y-axis. It's possible for some curves to trace over themselves. We'll see examples of that. So if you say, oh, wait a second, we drew this picture, but we seem to be missing things. Well, you're not missing things, it's just running over itself twice. And that can run into problems when you're doing things such as area. So you have to be aware that such things can happen. On the other hand, some curves you have to sort of do multiple passes around. So in other words, one revolution is not enough, not sufficient to close back up. You may have to do a couple revolutions, and it may never close back up. All right, so those are some notes, but let's do some practice. So, sketch r equals 1 minus cosine theta. Aha, that sounds familiar. All right, now, here's how I would recommend doing these types of problems. I would say, before you get into polar, this is not polar, but I'm going to draw something where I'm in the theta r plane. So I'm going to think of it like you have the xy plane, but now the input is theta. That's what will be the horizontal axis. The output is our vertical axis. And I want to ask the question, what does 1 minus cosine theta look like? How does it behave? Now, we can build up to it. So if I just had cosine, let's talk about cosine. Cosine does this in one revolution. So this would just be cosine. What would minus cosine do? It would flip it upside down. So this is minus cosine. Now what does adding 1 do? Shift. Which way? Shifting up. Vertical shift. So r equals 1 minus cosine theta. We'll start at 0, go up, and then it'll come back down after a full revolution. So here's 2 pi. So what are some interesting points? If we go into our mantra, zeros, maxes, mins, what are interesting points?
Only 2 zeros at 0, every 2 pi.
Right. And it's 2 pi periodic, it repeats, so we only need to go 1 revolution around here. Where am I maximal? Where am I farthest away? At pi. And at pi, what's my radius? One minus cosine pi, also known as? You're thinking 1 minus cosine squared. But 1 minus cosine pi? 2. Okay, so it turns out not very many interesting points, but that's okay. That's okay. Will I have symmetry across the x-axis here? Just a question for you. In other words, will it be the same up-down?
No.
And why is the answer yes?
Right.
So the question here, if you want to know if you're the same up, down, if I go a positive angle, do I get the same result as if I go a negative angle? So think about what happens when you plug in negative theta. What's true about the cosine function? It's not a very odd function. People would say they're keeping it level. It's even. It's an even function, so if you plug in a positive angle theta, you get the same thing as if you plug in a negative angle theta. So there will be that reflection going on. All right, so here's some interesting points. Well, the only truly interesting ones are at theta equals 0, we're at the origin. At theta equals pi, we're at 2. Just for fun, where are we at pi halves, which is our straight up? So if you plug in pi halves, 1 minus cosine pi halves.
0.
Well, it's 1 minus 0, which is 1. At theta equals 3 pi halves or negative pi halves, what do you get when you plug it in? 1 minus cosine 3 pi halves or 1 minus cosine negative pi halves, we get 1. So what's the curve doing? We start at the origin, and then we start getting further from the origin as theta. So as our theta is we're pivoting. Pivot, pivot. There's a TV show called Friends, and Ross was getting pivot, pivot. He's trying to tell people how to get that couch. He just kept saying turn, turn, turn. That's what we're doing. We're turning. And as we pivot, we're moving in a different angle, but we're moving farther out, and we're getting farther and farther and farther until we get to here. That's the furthest we get. And then what's going to happen? We're going to do the mere opposite. We're going to start getting closer and closer. We're pivoting in, and that's the shape. It's not perfect, but it's pretty good. And pretty good is good enough. Now this has a particular name. This is called a cardioid. So if you ever see a problem that says, oh, it's a cardioid shape, that's what it's referring to. Why do you think they call it a cardioid? It's a heart. If you turn this 90 degrees, it looks kind of like a heart. Close enough, close enough. So, all right, so that's that curve. Okay. Sketch R equals 4 sine 3 theta. Oh, this one's going to be good. Okay, so first off, if we're not sure, we'll come back and we'll do the same thing we did before. Theta R. Think about what's happening with the function. So sine, okay, we can guess what sine does. What does the 4 in front do? That 4 does what to your sine function? It will stretch it vertically. Okay, that's not so surprising. What does this 3 do? It's affecting your inputs. And how do we know it's affecting the inputs? Because it's in the input slot. So, is it smushing it or is it stretching it? It's smushing it. So normally, it would take us 2 pi to get all the way around. How long does it take now to get, quote unquote, all the way around, go through a revolution? Well, not as long, because we're going through our x's much faster. So, if I have here 2 pi, I can think of chopping it into 3 parts. And what's going to happen is I'm going to do a full up and down on each of these. So let's see, here we'll say this is 4. Let's say this is negative 4, and so this is our 4 sine 3 theta. Okay, some interesting points. What are some interesting points? Okay, 2 pi is interesting. It's probably a lot more interesting than just 2 pi. Can you tell me where the zeros are? They're nice and evenly spaced. One of them is at 2 pi, which is the same as 0. Where's the next one? 5 pi over 3. 5 pi over 3? That'll be that pi over 3. Yeah? How about from the start? Where's this one? Pi over 3. Here? 2 pi over 3. Here? 3 pi, 4 pi, 5 pi. Okay, so you might recall I said, when you have zeros, and this is really true when you cross, it's very convenient to mark these with dotted lines. You should think of these as behaving like asymptotes. So we have a 0 at theta equals 0. Pi over 3, that's like a 60 degrees. 2 pi over 3, that's over here. Pi over 3, 3 pi over 3, that's here at pi. 4 pi over 3. And 5 pi over 3. All right. Roughly speaking, we've chopped up into 6 parts. A little bit off, but roughly speaking. Now, let's just talk about this segment right here. From 0 to pi over 3. We start at 0, then we do what? We go out, and then we go in. Right? Because that's telling us start at 0, go out. In fact, this is at a distance of 4 here. This length is 4. And what's the angle? You can read it from the picture. What's halfway between 0 and pi over 3? This is at pi over 6. We're maxing out. So we go out, we come back in. That's the first up, down. Yes? Just think, go out, come back in. Now, for the next interval, so I'm going to say, focus on this part. We're at pi over 3 to 2 pi over 3. So we're up here. What do you notice about the sign? It's negative. Now, if it were positive, we'd be drawing up here. If it's negative, where are we going to end up drawing? Down. We're going to go opposite. So if this is a positive, then opposite is down here. So what's happening is we're coming in, and then we're going to go down and back up. And this part right here, this would be halfway between pi over 3 and pi halves. This is theta equals pi halves. Okay, now we're into this second part here, this second up stretch. So we're at 2 pi over 3 to pi. What's our sign? Positive. So we're starting at 0. We're coming off, go out, come back in. That's the second part. Now, the fun begins. We're at pi. So we're in this block right here. Between pi and 4 pi thirds. What's our sign? Normally we'd be in here, but our sign is negative, so we go across. And if you follow it through, it will actually trace itself twice.